what have we learned? We've learned that the 1s wave function, 2s wave function, 3s wave functions, and in fact all s wave functions, or L equals 0 wave functions, all of them are spherically symmetric. They have no angular dependence. Remember we said that in general the wave function depends on r, theta, and phi. S wave functions have no theta and phi dependence in them, unlike p wave functions, which we'll look at very soon. All right? Also, very important here, the probability density of all S wave functions is a finite value at r equals 0. Okay? Those are the two important things, and you know how to solve now for a radial node. You set the wave function equal to 0 and solve for the value of r that makes the wave function 0. Okay, now we have to continue this discussion so we can start to talk about the probability of finding an electron some distance from the nucleus. We just talked about probability density. We haven't talked about probability yet. And here comes probability. We're going to plot something, and we're going to talk about something called the radial probability distribution. What's that? Well, the radial probability distribution is the probability of finding an electron in a shell. You know what a shell is? You know, a shell is a sphere, but the sphere is hollow, except that, you know, at the diameter, right, or at the circumference, you have a thin coating. That thinness has got a dr to it. All right, it has a thickness to it. I'm sorry. It's a probability. This radial probability distribution is the probability of finding an electron in a shell of radius r and a thickness dr. So let me try to explain that some more. Here is this gray part. That's my probability density that I drew before, the dot diagram. This is a 1s wave function. This is the probability density for the 1s wave function, psi 100 squared. This blue thing here is a spherical shell. It has some radius here, r. It also has some thickness, dr. You see I cut away here, this thickness, dr. The radial probability distribution is the probability of finding this electron in this spherical shell that is of radius r and thickness dr. So it's the probability of finding the electron at some distance r to r plus dr. That's the radial probability distribution. Now, I want you to notice what is the volume here of this spherical shell? Well, that volume is just 4 pi r squared, the surface area of that spherical shell, times the thickness, which we're going to call dr. That's the volume. So now, if I wanted a probability of finding my electron in a S wave function, some distance from the nucleus, some distance r to r plus dr, what am I going to do? Well, I'm going to take my probability density, which I said was psi squared, probability per unit volume. I'm going to multiply it by a volume. Then I'm going to get a probability of finding my electron some distance r to r plus dr from the nucleus.